Hello everybody, welcome back. So in the previous lecture we were talking about the earthquakes and then how earthquakes can be predicted, and then we talked about something related to the fault motion or the plate motions and the creeping of along the Hayward fault. Now let us move ahead and see that how the earthquakes are measured and what is the importance, why we want to understand more about the earthquakes and all that. Okay, and few slides which we were talking about in the previous one, that since if we know the location of the fault lines along which the earthquakes are likely to be triggered, then we can go for better constructions along those fault lines or close to those fault lines. So we need to know the location, exact locations of the fault lines. Now as I was discussing that we have now the GPS stations in most of the along the seismically active regions. So that can help us in understanding that in which direction the plate is moving and at what rate the plate is moving. So this is an example which has been shown where we have the motion of the Indian plate which is moving in north-northeast direction, and then the part of the Tibetan plateau and the portion here, it is not exactly moving in this direction, but it is getting extruded. Okay, so there is an extrusion of the Tibetan plate and the part of the Eurasian plate here. Okay, so this is the boundary between the two plates, that is your Indian plate and Eurasian plate. This is what is the active plate boundary which goes over here like this actually. So this, and the further down here towards the south, it will be in subduction zone. There is a collision zone where two plates are colliding with each other. So strain is getting developed here and periodically released along various fault lines, okay, in this region. Now earthquake prediction, further if we take, people have tried and had few successes in this. So earthquake precursors which many scientific groups have considered is that they will try to look at the suspicious nature of the or the behavior of the animal before the earthquake. Then unusual electric signals which have been noticed again because of the electromagnetic waves, and in the beginning we were talking about that there is an magnetic field which has been generated by the inner core. So there will be some disturbance of the electric signals in the atmosphere, so that can be measured. Okay, then many large earthquakes are preceded by small earthquakes called foreshocks. Okay, so this is before a major earthquake, there will be series of small magnitude earthquakes which are termed as foreshocks. So if you closely monitor this, then you can try to predict that there may be a bigger event in this particular region or along a particular fault line. But this all, if you take the suspicious behavior of the animal, unusual signals and all that, they are all short term predictions. Okay, so you can have window is very short where we can predict, but this of course you will have to very precisely keep on monitoring the earthquakes, okay, through using high resolution seismometers. Chinese authority used series of foreshocks as a warning to anticipate the Haichin earthquake of 1975. Okay, so they were been able to identify or predict this event, okay, and saved a lot many people in that region. Okay, so in short, there are few successes, okay, in terms of the prediction of an earthquake, but still a lot of work is going on to have an understanding that how best we can use the precursors which can tell us that there may be a big event in coming future. Okay, of course GPS is one of the best way to understand which area the strain is getting accumulated and which area the strain is less accumulated. Okay, so we can at least say that the area having high strain will produce a large magnitude earthquake in near future. Then one can also have the probabilities, that what are the chances of having the earthquake in that particular region along the plate boundaries or away from the plate boundaries and all that. Okay. Now, along with the earthquake, definitely this is the most important part, because we need to know and identify the signatures which are of the such displacements which are taking place along the plate boundaries or away from the plate boundaries. So, if you look at that, the point at which the earthquake is triggered subsurface is termed as focus, and then the point exactly on the surface above the focus is termed as the epicenter. Okay. And the surface manifestation where the displacement has occurred is termed as the fault trace, and the landform which is developed because of the displacement is termed as fault scarp. Okay. So, this we will see when we are talking about the active faults and all that. So, you will be able to understand. So, what in short happens is that if you look at this layer and this surface and this surface were together at the same level before an earthquake. Okay. So, they were over here, but got displaced during an earthquake. Okay. So, this sudden displacement resulted into the release of an energy which was stored within the rocks, and the displacement occurred along the weak zone. Okay. This is what has been just shown, the same part, that is, we are having either we call this an focus at which the energy is released along a fault plane, and the exactly the point on the surface above the focus or the hypocenter is termed as epicenter. Now, along with the main shock, okay, we will have many aftershocks over the foreshocks which have occurred here. Okay. Now, this type of studies have been done to know that what is the extent of rupture which occurred during a particular earthquake. Okay. So, this is an example which has been given of an earthquake of Bhuj, magnitude 7.7. So, this was 2001 Bhuj earthquake. The main shock has been shown here, and these are all focal mechanisms which are showing is the aftershocks. Okay. So, with the help of this, one can also identify then how deep was the fault triggered. Okay. So, you can identify the depth of the fault, the earthquake, at what depth the earthquake was triggered, and how much area it covered in terms of the extent here. Okay. So, one can also look at, for example, if you look at this one, then whether the whole fault got ruptured or it was partly, some portion was only ruptured here. Okay. So, that one can make out here. So, recurrence of earthquake due to stress developed by tectonic forces, what we call the. So, this is another very important part which we need to understand, the triggering stress. Okay. So, what we see is the small part of the stresses are released which were accumulated slowly when the earth's plate moved towards or past each other. So, either they were moving towards each other, or they collided, or they slipped past each other. Okay. Since the earthquake drops the stress, okay, or the strain which was accumulated on the fault which slipped, the earthquake will not recur until the stress is rebuilt. So, next earthquake will not be triggered on that particular fault unless the required strain or the stress is built up along that, and typically it may takes hundreds or thousands of years. So, we know that at least in the Himalaya we have hundreds of years of recurrence between one earthquake and another, but this recurrence is on a particular fault. So, if you remember or recall the slide where we were looking at number of fault lines in the San Andreas fault system, where we have many fault lines having different slip rates. Okay. So, for on a particular fault, it will have typical of the recurrence, which may vary from hundreds to thousands of years. Okay, but once the stress is dropped, it will take time to rebuild. Okay, that stress. Okay, and to the next until the next event. Okay, but so you can remember that the diagram which we're talking about, that this is the period over which the stress will build up and this will be dropped here. Okay, and then we are having again building up and then drop here. So these are the events which we are having. Okay, now further, but an earthquake will occur elsewhere at the site other than the slip fault. Okay, so along a particular fault, if there is an earthquake which has been triggered, but the another fault line which is there, it may have potential of triggering the earthquake in near future, but this will take more time to have another event than compared to this one. For example, this we say A fault and this is B fault, then if the earthquake has been triggered here, so this will take time to recur again, whereas the B may have potential of triggering an earthquake. So if we have the GPS station close by, we can understand that what is the strain which is getting accumulated in this particular region. So now finally what we say that the area where the stress is building up will be the site for the next earthquake, okay, to occur, both large as well as small magnitudes. So this is what we can talk about. Now location of earthquakes, particularly what we use, the instrument is termed as seismograph. Okay, and then we are having the information on which has been collected, that is on the paper or a graph, which is termed as seismogram. Okay, where we measure or we identify the arrival time of P and S wave, and then we take the time difference between the P and S wave arrival, and then also we look at the amplitude of that, which can help in identifying the earthquake. Okay, so whenever there is an event, you will have more of zigzag lines here, which we say the amplitude of the P and S wave. Okay, so this is one of the seismograph which explains that how Richter scale is helpful in identifying the magnitude or knowing the magnitude of the region. Okay, so you are having the P wave arrival, because the P wave is the fastest, it will arrive first, and then you are having the S wave which came in. Okay, so there is a time difference between the arrival of S wave and the P wave, which is around 22-24 seconds here, and this is what is measured as the amplitude of the S wave here. Okay, which is around 23 mm. Now with this, Richter developed a logarithmic scale and then had an magnitude. So if you have that is the difference between the arrival of P and S wave, which is around 24, and then you are having the amplitude, which is around 23. So you connect this line, you will get the magnitude of that particular event. Okay, but now this computation is so fast that in no time you will receive a message or an email if you have registered on the USGS site, depending on that what magnitude earthquake information you would like to have, then immediately you can have that in a couple of minutes, having that information that what was the magnitude. So this is now has been done very fast with the help of computers and the programs or the softwares. Okay, now this is a concept what has been shown, that how we can identify the epicenters. So again, you are measuring the that at different locations you have different stations, and you have the seismographs which are measuring the arrival of P and S wave. So with the help of that, you can make out that what will be the epicenter of that particular earthquake. Okay, so at least 3 stations are required to pinpoint the coordinates of that particular event. Okay, so this shows that the curves which are available, okay, which shows the P wave arrival time and the S wave arrival time, and this has been like from different seismic stations. So seismic station 1, seismic station 2 and seismic station 3. So based on that, the distance of to the epicenter has been picked up. Okay, so you will get the distance from this one here. So you have this curves which we'll talk about, and then you just put the arrival time, and then you will get the distance, corresponding distance here. Now with the help of that, you are putting the circles, and the intersection of that circle, 3 circles, okay, will give you the point which is your epicenter of that particular region. Okay, so this is again the same, which shows you have the curves which are available, and here they have just put the different arrival times of different from or the data which has been put from the different stations. Okay, you are having one station here, so this is the P wave arrival time, this is an S wave, so the time is here which is equal to 900 kilometers, and then you are having the 3 minutes which is around 1800 kilometers, then 5 minutes 2300 kilometers. Okay, so based on this you put a circle of different areas, and that will give you the from the station, that particular station you will put in circle here. Okay, so this station, that is an SSPA, had in 3300 kilometers of distance, so you have in circle that is a green line coming in. Similarly, you are having this TEIG 900 kilometers which comes here, and then 1800 TEIG which is giving in. So this will be an intersecting point. Suppose sometime that you're not having the intersection exactly here, so in between points will be taken, and that is nowadays will be given as a tentative epicenter, but as and when more data comes in, you can revise and have the precise one. Okay, so this is how the epicenter has been measured. Again, this is a very fast process, and in no time you will get the information on your mobile, or either in form of the email and all that, where is the epicenter and what was the magnitude and all that. Okay, so this is one very important aspect which has been used to identify the fault rupture. Okay, and all the earthquakes which have been triggered after the event are been measured and taken into consideration to know the rupture length, that how far the rupture extended laterally and as well as at the depth. Okay, so this is what has been termed as the Vedati-Benioff zone. This is just to show that focus, but this is the pattern which has been seen, that in the subducting plate you will have the earthquakes which are been lined up to the greater depth. Okay, and which can go up to around 700 kilometers. Okay, so it can go up to 700 kilometers, and this process, okay, that is Vedati-Benioff zone, has been termed where a subduction boundary where the two plate converge, okay, at an oceanic trench, a cool oceanic plate, because the oceanic plate which is subducting down will be cool, but similar process has been seen when an earthquake has been triggered. Okay, but particularly with the Benioff zone, what it says or this suggests is that cool oceanic lithosphere is pushed down into the mantle. Okay, now because the subducting plate is cooled compared to the what the temperature it has in the subducting area, it remains brittle as it descends and thus fractures. Okay, now fracturing will trigger the small earthquakes, small magnitude earthquakes, and this zone is defined as a zone of earthquakes with increasing focal depth, because the depth is increasing slowly. So plate is going down, it is fracturing and triggering the earthquakes, and so focal depth will increase over the time. Okay, and that is termed as the Vedati-Benioff zone. And as I told, that it extends the focal depths of the earthquake in Vedati-Benioff zone can reach up to as deep as 700 kilometers. Okay, so this depth, measurement of depth, is extremely important when we are talking about the earthquake, because shallower earthquake will be more dangerous as compared to the deeper earthquakes. Okay, so this is an exercise which was been done for the 2001 Bhuj earthquake, where you can see this different sections which are been prepared. This is in plan view, which shows the how the area on the surface, how far it was been covered. That this is a main shock here, and you are having the other smaller earthquakes, aftershocks, which have been triggered here. Okay, and this is the depth sections, which shows that how deep was the earthquake which was triggered. So you can see here the maximum depth is around 25 to around 30 kilometers, and the main shock was around 25 kilometers. Okay, so this section again you see the depth section and the surface. So you are having the main shock here, and then aftershocks which are been confined in this zone. Okay, and based on that they have drawn a line which they say that this is an fault planes along which the earthquake occurred. Okay, so this is how you can identify the depth of an earthquake, how deep it was, whether it was shallow. But if you look at this one, there's again we say it was a very shallow earthquake of 2001. Okay. So classification of earthquake on the basis of the focal depth, if we look at, okay, focal depth of an earthquake is the depth from the earth's surface. Okay, so it is the depth from the earth's surface to the region where the earthquake energy originates. Okay, so that is the point, that is the focus from where, or the hypocenter from where the energy was originated, okay, or released. So most earthquakes occur in brittle portion of the earth crust above the brittle ductile boundary, and the boundary between the lithosphere, which is the between lithosphere and ionosphere. Okay, and then earthquakes with focal depth, if you have to classify this, okay, so about 70 kilometer depth if you take, are classified as shallow earthquakes, and if you are having around 70 to 300 they are intermediate, and more than 300 to 700 kilometers, okay, are the deep earthquakes. Okay, so as I told that this is extremely important to know that what is the pattern of earthquakes, whether it is intermediate or it is deep earthquake in any particular region, basically along the plate boundaries. It is extremely important to know that, as I told, that shallower earthquakes will be more damaging as compared to the deeper earthquakes or the intermediate earthquakes. Now this is what is another most important part is that when an earthquake has been triggered, it will result into the strong ground shaking. Okay, and in some places, depending on the material, okay, what type of material we have, that is the lithology what we say, okay, the amplification will be experienced in a different form. Okay, so for example, if you are having hard igneous rocks, and you are so you will have lesser amplification of the seismic waves, but if you are having sedimentary rocks, you will have little more, and if you are having loose material, what we call the alluvium, and further the finer deposits, we may have very high amplification. Okay, so the ground acceleration in powerful areas are the regions where we are having like which are sitting away from the epicentral regions. Okay, so most of the P and S waves what we see, okay, are having frequencies ranging from almost 0.5 to 0.5 to 20 hertz. Okay, so this is one very important part which you should remember. Okay, so the surface wave in particularly, what we are having, the L and the R waves, that is the Love and the Rayleigh waves, often have less than 1 hertz of the frequency. Okay, so this have the range 0.5 to 20 hertz, so very wide range is there, but this is having very less than almost like 1 hertz here. So during an earthquake, wide range of frequencies are produced. Okay, so we have like what we see here, 0.5 to 20 hertz. We are seeing that different very wide range of frequencies have been produced. Now, shaking results by high frequency. Okay, that is the 0.5 to 20 hertz waves will cause short building to vibrate. Okay, so the shorter buildings will be affected by the body waves. Okay, whereas the low frequency waves, this is the what we are talking of, the surface waves, will cause high building to vibrate. So if you are in the epicentral area, you will definitely have both all the frequency waves which have been generated, and so you can have the vibration of the shorter buildings as well as the taller buildings also here. Okay. Now it is the shaking or the vibration that causes the damage to the structures. So near epicentral or within the epicentral region, both frequency, that is high and low, so both high as well as low frequency waves will be experienced, hence both shorter as well as the taller buildings will be damaged here. While with the increase of distance, because there is an epicenter and then the waves will travel farther away, so as you have the increase in distance, high frequency waves will die out actually. Okay. So the body waves will die out and get weakened. This process is known as attenuation, whereas low frequency waves, okay, which are still there, which we say that okay 0.5 and then less than 1 hertz, what we are having, travel long distance without much of attenuation. So the surface waves will travel much farther, okay, and damages the tall building located even far. Okay. So we say that okay fine, we are not in the epicentral zone, so then we won't be affected and we can have high rise buildings if you are sitting far away from the epicentral region or the source region of an earthquake, but that is not true. The taller buildings will be affected by the surface waves, mainly having frequency which is less than 1 hertz. Okay. So this is one of the important part which you should remember, that the different frequencies waves are been generated during an earthquake, and which will affect the taller as well as the shorter buildings. Okay. So I'll stop here and we will continue with more details in the next lecture, talking about the different type of earthquakes in different region, that is what we call the interplate earthquakes and intraplate earthquakes, and then we can also talk more about the magnitude and the intensity scale. So we will continue in the next lecture. Thank you so much.